Let's talk about section 5.6 today, the inverse of a function. So the first thing that I want to show you is how to find an inverse of a function, and then I will show you what it is and what it looks like. So when you have a function, what you do is you do a few steps to convert it to its inverse. First step, you take the function notation, which in this case is f of x, and you replace it with the letter y. The next thing you do is you exchange the locations of your variables x and y. So this will become x equals 3y minus 1. And then the last step, well, second to last step, is you solve for y. So this will be easy to do. And you could, of course, write this any way you want to. But what I have here is basically 1/3 x plus 1/3 equals y. At that moment, we actually have the inverse, but there is a certain notation for inverse. So I would say this would be the last step. So I'm just going to move this y over here. I'm going to reverse the order of my equation just for looks. Okay, but instead of writing y, there is notation for an inverse, and it is this. That's your notation for an inverse. Okay, now what I'm going to do is I am going to put that into Desmos and show you the significance of an inverse. So now I'm going to move over to Desmos, and you can see right now I have graphed the original function. Now I'm going to move back over here. Sorry. And it's 1/3 x plus 1/3. All right, so 1/3 x plus 1/3. I need to go to my keyboard to do this, so hold on a second. 1/3 x plus 1/3. Okay, so be y equals 1/3 x plus 1/3. Now, let me see if I can change both of these into tables. All right, now by doing so, I have highlighted some points on this graph. And if I highlight some other points here that may be significant, let me see here. Yes, I've got some pretty good points to show you here. Let me remove that one. Okay, so we've got some points to show you here. Let's just use these sets here. Do you notice that this point that is on the original function, its coordinates are the reverse of what you see on the inverse? And look at these 2 points here. They're kind of like mirror reflections of one another, aren't they? 2, 1 and 1, 2. Well, that's interesting because an inverse is a reflection along the line y equals x. I don't know if I can change that color. Well, this line right here is the line of symmetry between the original function, which is in black, and this inverse function here. You know you have an inverse if you see this occur. Now let's go back to the lesson. Let's put this into practice. So here's 3 questions. I want you to find the inverse of each and graph them to make sure that you have accomplished that task. All right, let's see how you did here. Number 4, let's get the inverse. So the first thing I do is I take it out of notation, out of function notation. The next thing I do is I exchange the variables. Then I solve the equation for y. And I write it in inverse notation. So this y right here will become my inverse notation. And it's x over 2 or 1/2 x. Okay, now if you go to Desmos and you graph the original function and the inverse, you will see that they are mirror reflections of one another, symmetrical with respect to the line y equals x. Now, I'm not going to go ahead and graph it, but if you did, you would see that. Let's go on to number 5. Okay, step number 1, take this out of function notation. I'll put a 1 in there in front of that x. Step number 2, exchange the place of your variables. Step number 3, solve the equation. So I'll subtract 1. Divide everything by a -1. And then finally, I'm going to change this notation into the inverse. Okay, and one more time, if you were to graph this versus the original, all of the ordered pairs have switched places. So the domain becomes the range. The picture of the graph would show a mirror reflection across the line y equals x. Finally, let's take a look at number 6 and see how you did there. Step number 1, take it out of function notation. Step number 2, exchange the place of the variables. Step number 3, solve the equation. Now at this point, I would multiply by 3. So we'll do a distributive property on the left-hand side. And then finally, what I'm going to do is I'm going to take this out of function notation and into inverse notation. Or I'm just going to place it into inverse notation, I should say. And once again, if you were to graph that, what you would see is that line is a mirror reflection of this one with respect to the line y equals x. Okay, let's move along. This is a quadratic function. So let's find its inverse, and then I think we're going to graph this to see what this looks like. Step number 1, let's take it out of function notation. Step number 2, let's exchange the variables. Step number 3, let's solve it. Well, I got to get rid of that exponent of 2. Don't forget, when you're solving with square roots, you do get a plus or minus, don't you? Finally, let's put this into function notation. Okay, now in this particular situation, we do have a limitation on something. It says that your x coordinates can only be greater than or equal to 0. So we're only going to look at the positive numbers and 0 on the x-axis, and that's because of the square root. Let's take a look at this information. So here's the inverse. Here's the original problem. They should be mirror reflections of one another with respect to the line y equals x. So let's go to Desmos. Got to clear out some of my graphs here. I'm going to leave that other one in there. And I'll put it back in a second. Okay, so I might have a problem here because this new toolbar down here. Okay, I'm gonna pause this for a second, everybody. Okay, so I'm back here. The first equation is y equals x squared. Okay, so we look at that. That's our original. And Desmos, you could probably even type function notation, but we don't need to. Now the other one is positive and negative square root of x. So for this next one, I'm going to put in y equals square root of x. And then I've got to put in the negative square root of x as a separate function. Take a good look at those graphs. And now what I'm going to do is I'm going to put in the line of reflection, y equals x. Get rid of the keyboard and take a good look at this now. Okay, so we really only need to be looking over here. But as far as this is concerned, we really are only concerned with the part of the graph over here to the right, or maybe just the first quadrant if you want to, but we could look at the whole thing. There's no doubt about this. This, you see how this line intersects with the curves? And it looks like everything's the same. It's almost like you took this green curve, which is the parabola, and just rotated it 90 degrees. And you have the inverse function. And keep in mind, all of the points here that are on the parabola, the original quadratic, if you were to take the x and y coordinates and reverse them, then you would have all of these ordered pairs on this curve. And that's what an inverse is, much like an inverse operation. All right, let's go on to this next one. This is a cubic. Can we find the inverse of this? I think we're prepared with what we've been doing recently to be able to get that done. So step number 1, let's take this out of function notation. Step number 2, exchange your variables. And step number 3, solve for y. Let's see what happens here. Need to get rid of that 2 next, don't we? So maybe we'll write this as 1/2 x over here minus 1/2 equals y cubed. And then from what we've learned, how do we get rid of y cubed? Well, we take a cubed root, don't we? Well, I don't know if I got enough room here. Let's see if I can move this over just a little bit. Okay, so the last thing I'm going to do is I'm going to take a cubed root. So I'm going to go ahead and write this final answer. And to save time, I don't think I'm going to graph it, but if you did, you would be able to prove that this inverse is the mirror reflection of our original equation right up there. So let's shrink this down a little bit more so we can see this. There we go. And then if you graphed it, you'd see it's the mirror reflection across the line y equals x. Okay, how about we try this one? There's step number 1. Here's step number 2, exchange the variables. Step number 3, solve. Okay, so if I'm going to solve for y, the first thing I should do is divide by 2. So over here it's x over 2 or 1/2 x. But we need to get rid of that square root next, so I think I'll square both sides of the equation, which will give me x squared over 4 equals y minus 3, and then add 3 to both sides. So x squared over 4 plus 3 is the inverse. Let's try some more. Okay, everybody try those 3 problems. Let's see what you end up with. Okay, I'm going to run through them pretty quick. Switch my variables. Now I'm going to solve. We have negative x equals y squared, square root, which is a plus and minus. So the inverse of this function is plus and minus square root of negative x. Now don't worry about that negative number underneath that radical, because if x were negative, which says up here, then it will work because 2 negatives make a positive. So we have real solutions. Let's go to number 8. Take it out of regular notation. Switch your variables. And now begin solving. Looks like we're going to need a cubed root. Okay, final answer to this. The inverse is the cubed root of negative x plus 4. Cubed roots, we're not worried about the domain being restricted. So that looks just fine. Okay, let's move on to the last problem. Let's take it out of function notation. Let's exchange the location of the variables. And now let's solve it. I think we should square both sides and then subtract 2. And then convert it into the correct notation. And there we go.